Okay, so let's start with a summary of last time. Last time we introduced the concept of virtual work, which we called delta W. And for a force I, it's equal to the dot product of Fi with delta Ri, where delta Ri is some virtual displacement. And this virtual displacement is in harmony with the constraints. I'll put in harmony in quotation marks. So what this virtual displacement allows us to do is to imagine changing the system or displacing it a little bit and then seeing what happens. So this imaginary displacement is in harmony with the constraints, so you can't move a mass through a wall or extend an inextensible rod. But you can move it in a way that's unphysical. For example, if it's a thing that wants to go down because of gravity, but there's nothing that's physically constraining it from going up, you can examine the problem by pushing it up, and that's a virtual displacement. The true displacement is the displacement that the object will follow as a function of time. So that's dr. Delta r is a virtual displacement. It's without the passage of time. It allows us to disturb the system in a way that eventually allows us to understand what is allowed and then get equations of motion. So this virtual displacement, or this virtual work, is done by all the forces. So in principle, the total virtual work would be the sum of all the little virtual works from each force. Let's say there are n forces, capital N. And that's going to be two different sums. One is a sum of external forces, and the other is a sum of internal forces. And in principle, let's say the sum of the external, well, in principle, they're sums over different indices. Oops. Now, we did a couple of examples last week where we saw that often the internal forces do no virtual work. And we did a couple of examples. For example, the normal force is a force that does no work because by definition it is perpendicular to some contact surface, and no virtual displacement is allowed that goes through that surface. So only virtual displacements that are parallel to the surface are allowed. But then, of course, the dot product that gives you the virtual work between the force and a vector that's perpendicular to it will be zero, identically. And then we also did an example of two masses on a rod. We found that the tension in the rod, which we would call an internal force, also cannot do work. At the end, I introduced the principle of virtual work. Which we'll call PVW. That says that the total virtual work on a system is 0 if the system is in static equilibrium. And so compare this to what you would have done in vector mechanics, where you would have said that the sum of the forces equals 0, right? That's Newton's second law for static equilibrium. The big difference is that this uses vectors. So the sum of the forces really is 3 different equations, whereas the top one uses scalars. And that's in line with our motivation to do classical mechanics without using vectors. Now these virtual displacement delta R's, we found that in general for classical mechanics we want to use a set of generalized coordinates so that if possible the coordinates can be independent of each other. And so that led us to defining the concept of a generalized force to go with these generalized coordinates. So what we did is we started to ignore internal forces. So these are forces of constraint, typically. But there are generally workless forces. Oops. Or even better, forces that do no virtual work. So once we ignored the internal forces and kept only the external forces, so the external force could be, for example, the applied force, the net applied force on a particle, we introduced the concept of generalized force. Which we labeled with a capital Q. And that was the sum over I equals 1 to n, where n is the number of external forces, of the dot product of an external force vector with di Ri by di Qj. And so each generalized force, you can think of it going with a generalized coordinate. It's not necessarily have the units of newtons, so it's not necessarily the dimensions of force, but you can think of it as sort of as like either a force or a torque or something that wants to make something move in the direction Qj. And then we were able to write that the total work then is the sum of J equals 1 to n, where now n is the number of degrees of freedom of qj, delta qj, so capital Qj. And note that there's no more vector product here, and this is a completely scalar equation. And then after that, I wrote down a procedure for solving statics problems using the principle of virtual work. I'm not going to rewrite the procedure down, but we'll do a series of examples now where you can see how we can use the virtual work to solve simple static problems and get a little bit deeper understanding of what these generalized forces are. Any questions so far? So we'll start with examples of solving static problems. With the principle of virtual work. So let's start with the example that's in the notes, which is example 3.3. So in this example, we have a pivoting rod the uniform rod, like my drawing. They can pivot at a point up here, which we'll use as the origin of our system. So let's have a y-axis going downwards and an x-axis going to the left. The rod has a length of 2 capital L. And it has a mass m. So we have gravity going downwards. And so the rod, its weight is exerted at the center of mass. And then we apply a force here at the other end of the rod, the horizontal force. And we ask, what is the magnitude of F so that the rod is in equilibrium for some angle theta. So the question is, solve for F. Given the angle theta. So step 1 was to determine the unconstrained number of degrees of freedom. So this is a rigid object. Okay. And so for a rigid object with no constraints, there are 6 degrees of freedom. Now, that's for a rigid object in 3-dimensional space. However, this is not free to move in three-dimensional space. So we identified a number of holonomic constraints that we have. So let's say, for example, if we wanted to choose 6 degrees of freedom to describe the position of this rod in three-dimensional space, you agreed that we could choose 3 of those coordinates to be the x, y, and z position of the pivot point, and then we can use 3 angles, let's say theta x, y, and z, to be the angles of rotation of the rod with respect to the axes x, y, and z. So if that were our choice of 6 degrees of freedom, then the constraints that we have are that, the holonomic constraints that we have are that x is equal to 0 because the pivot point is fixed, y is equal to 0 for the same reason, z is equal to 0 for the same reason, and then the rod is constrained to swing in the xy plane, and so we have the angle about the x-axis is equal to the angle about the y-axis, which is equal to 0. So we have 5 holonomic constraints. Thus, we only have 1 degree of freedom. And of course, we'll choose theta from the figure. And the notation would be theta z. Okay? And so that's actually step 3, is to choose the coordinate. Now we identify the forces that can perform virtual work. So both F and mg, yeah, there's a question, Michelle?
Hey, yeah. Does that mean that the rod pivots out towards us in the z direction?
Well, it's not a great.
I'm sorry, what?
Theta z is the axis is coming towards you out of the page. The rod is rotating so that the angle changes towards the draw. Switch it vertical.
We're having a tough time hearing you.
Sorry?
Yeah, could you repeat that? I didn't hear you.
Okay. Yeah, I think it's best to speak because it picks up on our way. So the rod rotates so that the angle theta changes, right? So another position of the rod is the dotted line there. So the angle, the z-axis points towards you, so out of the page, and then the angle that the rod makes with, with respect to the y-axis as it rotates about the z-axis is theta. This is like overly complicating a simple problem, but it's just to get the general idea of 6 degrees of freedom being reduced to 1. In this particular case, right, it's fairly obvious that there's only 1 degree of freedom and that the whole rod is described by the angle theta. I just wanted to show you that, you can start off with 6 degrees of freedom, write out 5 holonomic constraints, and then conclude that you only have 1 true degree of freedom. So the forces that can do work are F and mg. can do virtual work. Now, if this were Newtonian physics problem, or you're going to solve it with the vector mechanics, then that's not the only forces on the rod, right? You have some reaction forces at the pivot point. And if you're using Newton's laws, you have to take those into account. And of course, if you're going to use first-year undergrad physics, you would, in fact, not use the forces at the pivot point, because you would realize that the easiest way to solve this is with torques, right? So then you would use the second method of, first-year undergrad physics, and then use torques. So that's already not a super beautiful way to do things, because you have to change the method based on the problem. But as we'll see with this virtual work thing, you automatically get torques. So the reason, back to the point here, which is to identify the forces that can do virtual work. So there's one reaction force at the pivot point, but the pivot point is fixed. So it cannot be virtually displaced. And so the virtual displacement at the pivot point is 0. So no matter what force you have at the pivot point, it cannot perform any virtual work. Okay? So the final thing now is to write out the positions of where the forces act in terms of the generalized coordinates. So what we need ultimately is delta R1 and delta R2 if mg acts at R1 and f acts at R2. So mg acts at a point, a vector, let's say, that we'll label R1. And similarly, f acts at a point which we'll label by the vector R2. So what we want are delta R1 and delta R2. And sort of intuitively, you know that those delta R's are going to have to be perpendicular to the rod, right? Well, let's work it out in painful detail. So the total work, right, is going to be mg dotted with delta R1 plus f dotted with delta R2. So what we want is we want R1 and R2 in terms of the generalized coordinate, which in this case is theta. Okay. So let me write out the vector R1. We're going to run out of page now. R1 vector. So the x component of the R1 vector, it's in the negative direction. And so it's minus L over 2 times sine theta is the x component plus cos theta y hat is the y component. Is that correct? Yes. Similarly, R2 is L, so it's minus L, sine theta x hat. Oh, sorry, the y component is actually positive. Sorry, so that's a mistake in the sign there. Only the x component is negative. Okay, so I've just written out the vectors R1 and R2 in terms of L and sine theta. L is a constant. So what we want now is delta R1 and delta R2. So delta R1, remember, is given by di R1 vector by di Q. There's only one Q, which is theta, right? Delta Q. That's the same as di R1 vector by di theta, delta theta. So if we look at our equation for R1, so that's d by d theta of an R1 we said was minus sine theta x hat plus cos theta y hat. And so taking that derivative, we get that delta R1 is equal to the derivative of minus sine theta is minus cos theta. Oops, and sorry, I forgot the L over 2 here at the front. I'll just put it in front of the derivative because it's a constant. So that's L over 2 times minus cos theta x hat. And the derivative of sine of cos theta is minus sine theta. So it's minus sine theta y hat delta theta. And so similarly, delta R2, the same math, is simply minus L times cos theta x hat plus sine theta y hat. Right? Now, we write out the total virtual work. Yeah, Michelle, you have a question?
Yeah, I thought we decided that the negative sign in R2 was a mistake.
Did we? No, I think it's in the before you take the derivative, the cos theta and the sine, and the x and y components have different signs, but after you take the derivative, they have the same sign.
Okay.
Because R1 and R2 are basically the same vector, just one is twice as long as the other, right?
Right. Okay.
So the total virtual work now is it's going to be the mg force dotted with delta R1 plus the F force dotted with delta R2. Delta R1 and delta R2 are both vectors. So mg, this force, the weight is mg y hat, right? And we have y in the positive down direction, or y positive in the down direction. Whereas F vector is the magnitude of F, and it's in the negative x hat direction. So when we do the dot products of mg and delta R1, of course only the y component matters. So the y component of delta R1 is L cos theta y hat, right? Or sine theta over here. Well, let's just write it out. So here we have mg y hat dotted with delta R1, which we said was L over 2. Oops. And then the only term that matters is this minus sine theta y hat. The second term was minus f x hat dotted with L sine theta y hat. And that's a minus L sine theta y hat. I believe. No, it's not the y hat that matters, it's the cos theta, it's the x hat. Right, it's this term here. And that's minus L cos theta x hat. So of course, the only vectors now are the hats, right? So x hat dot x hat is 1 and y hat dot y hat is 1. So the first term becomes L over 2 mg sine theta. And the second term, it's with a minus in front. And the second term is plus L f cos theta. I guess both of these terms I forgot to include the delta theta. Of course, since we're setting it to 0, it won't matter, but let's put it in for consistency. And now we have static equilibrium if the total work is 0. So we set this equal to 0. Of course, the delta theta now we don't need to keep. The L's cancel, and we have f cos theta equals 1 over 2, sorry. mg sine theta. Or f equals a half mg tan theta. So that looks like it was a server crash. For once, not my fault. I'll have to wait for everybody to rejoin here. Well, that was annoying. Let's give people a minute to reconnect. I bet their server crashed, and hopefully people didn't give up trying to connect. Did everybody get kicked off, or was anybody on like the whole time?
No, it looks like everyone got kicked off.
I'm the only one who got kicked off?
It looks like we all did.
Oh, I see. Okay. Let's give it a minute then. Well, I bet some people might have given up. All right. Well, let's continue, I guess. Jimmy, still missing a couple of people here. Actually used Collaborate all last year and I never had a problem with it. This year it's been a disaster. We're still missing Michelle and Jason and Kevin. Were you guys in the classroom with them, or?
Me and Daniel are in the classroom, but they're coming in from somewhere else.
Okay. Just email Michelle. All right, well, let's resume. So what we did here is we wrote out the total virtual work, and we got an equation that looks an awful lot like the equation for torque. If you have this equation here, it almost looks like an equation for torque. All right, you have this L over 2 mg sine theta. That's the torque of mg exerted at a point L over 2. Right, and then you have this LF cos theta, which is the torque from the force F. So this sort of general method gave us, in fact, the torque equation. And so the problem is solved. Now, I did mention in the procedure that we had an alternative way of solving the problem, which was to evaluate the generalized forces and to set them equal to 0. So let's do that just for completeness. So step 7 was setting it equal to 0. And now let's look at step 8, which was the alternative, is to solve the problem by setting the generalized forces equal to 0. So the generalized forces, Qj, there's only going to be one, right? It's the sum of I equals 1 to 2, because we have two forces, of Fi dotted with di Ri by di Qj. And so that's, of course, what we've already evaluated. The di R1 by di theta is this term that we had up here. So it was L over 2 times minus cos theta in the x hat direction minus sine theta y hat. Right? So let's copy that down here. So di R1 by di theta is L over 2. I guess I can put the minus sign at the front. Cos theta x hat plus sine theta y hat. And similarly, di R2 by di theta is minus L times cos theta x hat plus sine theta y hat. And so the generalized force, Q, so J stands for the theta, there's only one J, so let's call it Q theta. So that's the first force, which is mg in the y direction, so that's again going to pick up, so it's a dot product, it's going to pick up only the sine theta component. So that's mg times minus L2 sine theta plus F, and that's only in the x direction, so that's going to pick up only the x direction. And F is in the minus x hat direction, right? So it's let me write that as minus F times minus L cos theta. And so then we find that Q theta is L times a half mg sine theta minus F plus the minus at the front here, and then a plus here F cos theta. And so this generalized force, Q theta, as you can see, it's actually the total torque. And so, just so I'll start a new page, I'll write on the side here that setting Q theta equal to 0 is the same as setting the sum of the torques equal to 0. And so we never even mentioned the concept of torque, but we recognize here that effectively the answer gave us how to do the problem with torques. Any questions? So let's do another problem. Example 3.4. In this case, we have a wall on the ground. And we have one mass that's attached to the wall. And it can slide up and down. We have a rigid rod and a second mass that's on the ground. The rod has a length L. The origin of the system we'll put at the corner here. So the two masses are constrained to slide on the surfaces. The top mass, now if we draw the forces that can do virtual work, it has a weight, mg. Let's say they're both mass m. And then we ask the question, what force F do I need to apply in order to have static equilibrium? Okay, so again, so now we have two particles. Oops. So in principle, there should be 6 degrees of freedom. But of course, we know that's not the case because there's several holonomic constraints. And those holonomic constraints now are, first of all, the system is constrained to a plane. So the 6 degrees of freedom could be x1, y1, z1, x2, y2, z2. Or we'll call the top one particle 1 and the bottom one particle 2. So our holonomic constraints are that x1 is equal to 0 because the mass 1 is constrained to the vertical wall. We have z1 equals 0 because it's not moving in the z direction. We have y2 equals to 0 because the bottom mass is constrained to move in the x direction. We have z2 equals to 0 because, again, it's a two-dimensional problem. And then we also have the constraint that the two masses are separated by a length L, or a distance L from the rigid rod. And so that gives us the constraint equation that y1 squared plus x2 squared equals L squared. So that's just the hypotenuse of the problem, of the triangle there. Note that this is wrong in the notes. In the notes I have it written as a 0, but it should be L squared. So again, we have 6 degrees of freedom, and we have 5 constrained equations. So there's only 1 true degree of freedom. And so let's choose the angle theta down here as our degree of, as our generalized coordinate. So now, of course, there are other forces that I haven't drawn, right? There's a reaction force on the vertical wall, and then there's a reaction force or normal force on the ground as well. But those forces cannot perform any virtual work because they act perpendicular to any allowed displacements. Mass 1 can only move up and down, so only forces that have a component that's up or down can do virtual work. And mass 2 can move only left or right, so only forces that have a left or right component can perform virtual work. So the total virtual work then will be the virtual work of mg plus the virtual work of F. So now we have to write out the components or the location of where mg and F act, which we'll call R1 and R2. And then we'll be able to find the variation of R1 and R2 with theta, and then finally write out the total virtual work and set it equal to 0. So the R1 vector is the vector of where force 1, or mg, is acting, and R2 is where the second force, which we'll call F, is acting. So the vector R1 is L sine theta y hat. And the vector R2 is L cos theta x hat. So now we need delta R1 and delta R2. So delta R1 is going to be L cos theta delta theta y hat. And delta R2 is going to be minus L sine theta delta theta x hat. And so that makes sense, right? The change in sign there. Delta R1, for example, if it's pointing up in the positive y direction, then the second mass on the ground, to move in harmony, must move in the minus x direction. So that's for increasing delta theta. Did I get kicked out again? Can you people still hear me? I'm seeing it's not updating. This is what happened last time. And it's done. Can anybody hear me? Oh, so you can still hear me. So it's just the one computer that got kicked off. Okay. All right, so we'll keep going then. So we've written delta R1 and delta R2. All right, so now we can calculate the total work, virtual work, W, is equal to the first force, which we'll call mg. And so that was in the minus y hat direction. And that's dotted with delta R1, which is L cos theta, delta theta y hat. And then the second force is minus F in the x hat direction, dotted with minus L sine theta d theta x hat. And so if we set the virtual work equal to 0, then the delta thetas will drop out of the equation. And if we do the dot products, we find that the total work is mgl cos theta with a minus sign plus FL sine theta. And here again, we could so if we set this equal to 0, we can also cancel the L's, and you can find that the force F is mg cotan of theta. Of course, the total virtual work there looks an awful lot like what you would get from solving the problem with torque. So just for completeness, again, let's work out the generalized force. So Q theta is going to be the first force, which is mg y hat, and that's dotted with di r1 by di theta, plus the second force, which is minus f x hat, dotted with di r2 by di theta. So that's a pretty much identical equation. And so di r1 by di theta is L cos theta. All right. Oh. So here you get minus mg L cos theta. And then the second term is going to be plus F L sine theta. And there again, that is equal to the total torque. So this generalized force is the total torque in this case. Lou, you're asking where is the delta theta? The delta theta is, there is no delta theta in the generalized force. Right? The generalized force, Qj, was the sum over the I forces of the external force dotted with di Ri by di Qj. The delta Qj comes in only when you do it by solving for the total work, where you carry around the delta thetas. So the generalized force is just the total work minus the where you remove the delta thetas. If you go back and look at how it was defined. And in this case, it's exactly the same math because there's only 1 degree of freedom. So let's finish with one last example, and then these technical issues we didn't get as far as we wanted. Page 5. So the last example is 3.5. It's going to require some drawing. We can just use so we have a sphere of radius r, and we have 2 masses that don't have any friction with respect to the sphere. And they're connected by a rope of length L. The mass on the left has a mass of 2m, and the mass on the right has a mass of m. If we put in a coordinate system at the center of the sphere, we can describe the location of the left mass with an angle phi. And the right-hand mass with an angle theta. So we only have 1 degree of freedom here, right? Because if you move one mass, it's going to pull the other mass along the surface of the sphere. And the question, of course, is to solve for the angle theta of equilibrium. So there's only 1 degree of freedom. And let's choose theta. What did I do everything with? Yeah. Let's choose theta. So theta and phi are related, right? The total angle subtended by the rope, right, is L over R in radians. So you have phi plus theta is equal to L over R. Just think about it in radians, right? That means that phi is equal to L over R minus theta. And that means that delta phi is equal to minus delta theta. So if theta increases, then phi decreases. So the only forces that act on the particles that are external forces that can do virtual work are gravity. Every other force is perpendicular to the allowable motion. So I'm going to go slightly over time here to finish this problem. So those two forces will, let's call the one on the, what should I call it? Let's call the one on the right mass number 1, and the one on the left mass number 2. And then let's write out the vectors R1 and R2 where the weights are applied, and that's the position of the two masses, right? So R1 vector is going to be equal to R times sine theta x hat plus cos theta y hat. And R2 is going to be R, so its x component is negative, minus, oops, and that's a sine phi, plus cos phi y hat. That means now if we want the variation, delta R2, or, yeah, no, we can take the variations now. So now we want the variations with respect to theta and phi, and then we can easily convert the variation in phi to variation in theta with our equation above here. So delta R1 varied with respect to theta is going to be R cos theta delta theta x hat minus R sine theta delta theta y hat. And delta R2 is going to be R minus R times cos phi delta phi x hat minus R sine phi delta phi y hat. And now delta phi, remember, is minus delta theta. So delta R2, if we write it in terms of our generalized coordinate delta theta, is R cos phi delta theta x hat plus R sine phi delta phi y hat. So if we now calculate the total virtual work, so that's going to be M1 with delta R1 plus M2G delta R2, where M2 is 2M and M1 is M. So in both cases, only the y component matters. So the first term, the weight is mg minus mg in the y hat direction. And that's dotted with the delta R1 in the y direction, which is minus R sine theta delta theta y hat. And the second term is minus 2mg y hat, and delta R2, its y component is R sine phi, oops, that's a delta theta up here. Delta theta y hat. Alright, so then that's equal to mgr sine theta delta theta minus 2mgr sine phi delta theta. Now, phi, remember we said, was equal to L over R minus theta. So that's sine of L over R minus theta delta theta. Now, this sine of L over R minus theta, we can use the double angle formula. Sine of alpha minus beta is equal to sine alpha cos beta minus cos alpha sine beta. So if I plug that in, then we have W is equal to mgr sine theta delta theta minus 2mgr. So here we have sine of L over R minus theta. So that is sine of L over R cos theta minus cos L over R sine theta. And that's got to be equal to 0. So if that's going to be equal to 0, that's a capital R. We can cancel the MGRs everywhere. And we can divide everything by theta. If we divide everything by theta, or by cos theta, sorry. Oops. So the first term and the delta thetas cancel as well. There's the delta theta there. So if we divide everything by cos theta, sine over cos is tan theta. Then we have minus 2 times sine of L over R. Oops. Plus 2 times cos of L over R tan theta. And so we can isolate this and find that tan theta is equal to 2 sine L over R divided by 1 plus 2 cos of L over R. And I'll let you work out the case or work out what the generalized force is, and it's in the notes. Sorry for going over time and for additional tech issues. If there's no more questions, we'll talk again on Wednesday. Thanks.